Hi, I'm Nathan Manning, and this is my partner Antoine Gravat, and our project is on the counting sort algorithm.
So, a little introduction to the counting sort algorithm is that it's an algorithm that counts the number of occurrences for specific values in an array and then performs some arithmetic on these counts to create a unique index into the final sorted array where a value will be placed. So, here's just a counting sort algorithm demo. So we're going to have an example array of integers, 5, 1, 3, 2, 8, 6, 1. So for step one, you're going to create a separate array that's the size of the maximum value plus 1, which holds the number of occurrences of a particular value in the index that matches that value. The array value should be initialized to 0 first, and then the count value should be set. Since the maximum value in this array is 8, 8 plus 1 is 9. So the second array size is 9, which means it has 10 indexes. Value 5 occurs one time, value 1 occurs two times, value 3 occurs one time, value 2 occurs one time, value 8 occurs one time, and value 6 also occurs one time. So for step 2 in the second array, which holds the number of occurrences of each value, you want to sum up the value at each index with the value in the index right before it. So if this is the second array, then the values of the second array after adding the current and previous index values together would be 0, 2, 3, 4, 4, 5, 6, 6, 7, and 7. So for step 3, you're going to create a third array, which will be the array that contains the sorted values. In order to insert the values into this array, look at the value in the first array, in this case 5. Then look for the index 5 in the second array and observe its value. In this case, it's 5. Therefore, you subtract 1 from this value to obtain the value 4. It is this value that you will use as the index into the last array to insert the specific value. Therefore, index 4 in the final array will have the value 5. Now you want to look at the second value in the first array. In this case, it's 1. Then look for index 1 in the second array and observe its value. In this case, it's 2. Therefore, you subtract 1 from this value to obtain the value 1. It is this value that you will use as the index into the last array to insert the specific value. Therefore, index 1 in the final array will have the value 1. Then you want to go ahead and look at the third value in the first array, which is 3 in this case. So then you look for index 3 in the second array, observe its value, which is 4. Therefore, you subtract 1 from 4 to obtain the value 3. And then it's this value that you will use as the index into the last array. So therefore, index 3 in the final array will have the value 3. Now you want to look at the fourth value in the first array. In this case, it's 2. Then look for index 2 in the second array and observe its value. In this case, it's 3. Therefore, you subtract 1 from 3 to get the value 2. And then you'll use the value of 2 as the index into the last array to insert the specific value. Therefore, index 2 in the final array will have the value 2. Now you want to look at the fifth value in the first array. In this case, it's 8. So look for index 8 in the second array and observe its value. In this case, it's 7. Therefore, you subtract 1 from 7 to obtain the value 6. And then it's this value that you use as the index into the last array to insert the specific value. Therefore, index 6 in the final array will have the value 8. Now look at the sixth value in the first array. In this case, it's 6. You look for index 6 in the second array, observe its value, which is also 6 in this case. So then you're going to subtract 1 from 6 to obtain the value 5. And then you'll use this index of 5 into the final array to store the value 6. So index 5 in the final array will have the value 6. Now you look at the last value in the array. In this case, it's 1. Then look for index 1 in the second array and observe its value. In this case, it's 1 because we previously subtracted 1 when we sorted the second item in the list, which was 1 as well. Therefore, you subtract 1 from this value to obtain the value 0. It is this value that you will use as the index into the last array to insert the specific value. Therefore, index 0 in the final array will have the value 1. As shown by the final array table, the original array has been fully sorted. As you can see, the values are 1, 1, 2, 3, 5, 6, and 8, which are all in ascending order.
For the time complexity of the sorting algorithm, it's linear, which means that it goes up proportionally with the number of elements. Uh, and also the best runtime for this algorithm is O of n, where n is the the number of elements in the array that needs to be sorted. And the average runtime is n plus k, where n is also, again, the number of elements in the array that need to be sorted, and k is the maximum value of the array plus one. The worst case runtime for the algorithm is O of k, where again, k is the maximum value of the array plus one. And overall, the algorithm is most efficient when the range of values in the initial array that's being sorted is not much larger than the actual number of values in the array. For the space complexity, it's also a linear space complexity. It's O of n, where n here is the maximum value of the array plus one. So it's the k value in the time complexity. This can cause some problems though, because if there's a large range of potential values and the array doesn't use much of them, then you're allocating large chunks of memory for the new array for basically no reason. Like it says here, even if there aren't a lot of values in the array that needs to be sorted, uh, the new array still needs the maximum potential value plus one. Some pros of counting sort are that it's faster than comparison-based algorithms. Like I said previously, the linear time complexity is great, and it makes predicting the speed of the algorithm 100% accurate. The algorithm is usually used as a subroutine for other sorting algorithms like radix. So by itself, it's not very popular, but when used with other sorting algorithms, it can be very powerful. It works best with integer data, but it can be used for any data, like any sorting algorithm. It's a stable algorithm, which means that duplicate elements in the array that needs to be sorted will retain their place relative to the duplicate elements in the array. So, like in our example, there was two ones. So the one that came first in the original array will come first in the second array. And a cool fact about counting sort is that it uses a basic form of hashing to arrange the elements into a new array. So, like Antoine said, some arithmetic is performed on the elements in the original array, and then those elements are placed accordingly into the new array. So that's a basic form of hashing. Some cons of counting sort are that you have to know the maximum potential value and the n value beforehand. So, I mean, that if you have large sets of data, that can become kind of tedious. Indexing the array, you have to use the maximum potential value plus one. Like stated previously, even if the array being sorted doesn't even get close to the maximum value. So that takes up large chunks of memory. You don't always need to use that memory that it takes up, and it's not an in-place algorithm either, which means that it has to allocate new memory for sorting rather than just using the memory that's already allocated for the array to sort it. So those are the cons. And that's our presentation.